Thank you very much for your kind words of introduction. Ladies and gentlemen, welcome to my presentation. We're talking about the re-establishment of passability by way of rock ramp fishways. And this was also the paper that I wrote. I'm an engineer. I know very little about fish, and therefore I needed Armin Peter and his group to support me. This is why his name is on the slides as well. I would like to present the results of my research and also the results of his or our research on unstructured rock ramps. In principle, we've got two types of rock ramps. On the left-hand side, the classical ones that are characterized by these different rocks. They cover the ramp completely, and they are either set properly or they are simply piled. This is a strong structure. They can be built up to a slope of 10%, but they're very stable. When the critical flow is reached and they're destroyed, they are fully destroyed abruptly. So that is quite dangerous in case of floods. And therefore, the second type of rock ramps was developed. There are the dissolved rock ramps. You don't have this carpet of rocks. There are these structured ramps where the rocks are set in line, so to speak, up to a slope of 5 or 6%. Then unstructured rock ramps, this is what I'm going to talk about later on, and ramps that are developed dynamically. The idea is to provide different types of material, gravel and rocks, and leave it up to the river to shape or organize these blocks or rocks on its own, and that could also cover a slope of up to 5 or 6%. And so this is a relatively good behavior in case of an overload. They are not totally destroyed in case of an overload, but they are adjusted. And this is an advantage for flood cases. But rock ramps are not fishways for upstream migration. First of all, we want to protect the bottom of the river against erosion to ensure that it remains stable during floods. Today, I'm going to talk about unstructured rock ramps, and I would like to define them on the basis of this beautiful winter picture. This is in the canton of Graubünden against the flow. And you see the rock ramp, which is characterized by randomly distributed rocks. There is no contact between the rocks. They are individual rocks. And there is no geometric structure. They are determined by 3 parameters. That is the diameter of the individual rock, 1.4 to 2 meters. They are huge and weigh about 5 tons each. On the other hand, that's the second parameter, the sediment material, the grain composition, and the density. That is the relationship between the total surface with rocks and the total ramp surface. This is 20 to 25 meters wide. This ramp is 100 meters long, and 20% is the density. But why should you think about unstructured rock ramps at all and do research? Well, it is a matter of river construction. We don't have any basis for dimensioning. And of course, you would like to expand the application. And what is very important, the ecological assessment of these rock ramps is missing. We don't have data to determine whether they're good or not. They look quite nice, they seem to be ecological, but we don't know whether they can be passed by fish. This is something that you've seen before. About 100,000 artificial barriers exist with a height of more than 50 centimeters. This is a clear barrier, and that was the situation in 2009, and passability is to be ensured. My paper covered 4 phases. The first phase is on stability, so that has to do with river construction. What would be the influence of the construction parameters and the optimal parameter combination to ensure stability, and then the behavior of the ramp. We did not only examine the ramp, but the ramp within the river system, what happens in other sections of the river. This was examined in the lab at the VAW. Third phase, that's kind of basic research, description of turbulences in these heterogeneous ramps, measuring speeds with a 2-dimensional LDA system. And I will show you a picture later on. And that was tested in a second lab. Fourth, field test. We did practical tests to determine the effective passability opportunities of these ramps, and of course field tests in a prototype. The general objective was to expand the basics for the determination of the dimensions, focusing on hydraulic and ecological requirements. Today, I would like to give you some important results, also with respect to river construction, if I may put it that way. Let's start with the stability. This is my lab channel, 13.5 meters long, 60 centimeters wide. You see the different instruments to measure water level, speed. Here you see the machine adding the sediment. And at the end, you also see a basket in order to weigh the sediment. You see how we built the ramp at the beginning, also in a cross-section, which is not that important. The inlet, the buffer section was necessary due to the channel. The slope was 5%. That's relatively steep for such a rock ramp with a specific sediment material and the size of the rocks. Then we charged the system with the same flow until balanced conditions were achieved, which meant that nothing is moving anymore and the ramp is stable. And in that case, I measured the slope again, and in the next step, we took a higher flow rate. So we were able to assess the erosion in the ramp, and for every load case, we were able to determine the balanced slope. As I wanted to, as we said before, we wanted to determine the optimum situation for 2 different sediment mixtures, fine and more coarse, in line with different regions. Then the more grainy material, which was interesting for research with or without sediment in order to determine movement. 3 different block sizes, my stones, and also 2 different densities. All of these parameters were optimized in order to determine stability. This is the final result of my paper. All these dots are different tests, and it's not very important to know which dot was which test, but this gives you an undimensional stability situation. This is the flow, and this is the characterizing feature of the ramp, sediment material, etc. And on this axis, you have the flow. So on the basis of this relatively simple formula, you can examine the dimension of the slope. 1.5% of the slope is efficient, so we need 650 of these parameters, and then you can play with this formula in order to determine the optimum ramp. I'm also going to talk about some basic research, and that's important because it's of relevance for the ecological assessment. This was a second channel. This is a picture. Here you see the rock ramp, which was fixed so that the geometrical situation was always the same. Here you see the LDA probe, the laser rays, 4 laser rays that meet at one point. And at that point, 2 speed components can be measured precisely, and thus you can assess the turbulences. On the basis of these detailed measurements, 5 millimeters in every direction, that is a good grid, it was possible to determine such cross-sectional profiles in flow direction. This is the width and this is the height of the channel. The points are the topography, that is the bed of the river. And this is the average speed over time. It is not important to know whether it's 2 or 1, but there are several gray layers. So there is a certain heterogeneity in each cross-section. And thus, the variety of corridors could be analyzed in such a way. So on the basis of different profiles, you can determine whether they are always heterogeneous, these rock ramps, or not. With the local flow speed, you can determine hydraulic plots. This is something you've definitely seen before. It's once again that cross-section. You take for example, one specific fish, such as the bullhead, and I read what speed was required, 0.07 meters per second, and anything that is more is red. So theoretically, the bullhead can't swim against it, and anything below is green. And if you do that for different types of fish with different speeds, the other fish, there it is a bit more, and for the trout it is even higher. So that was bullhead, roach, and trout. And thus you can, in theory, analyze the passability of such a rock ramp. If all cross sections give enough green, theoretically it would also be feasible for the trout. This is what we did in the lab. And now our actual field tests. Those were conducted in particular by Armin Peter and his group without my support. This was the functional check of such rock ramps. The idea is to catch fish above the ramp, to equip them with the pit tags, two different sizes, of course, for different fish, or mark them with colors, and then catch leave the fish or stock them below the ramp. And you would want to determine whether they managed to reach the section of the river above the ramp. This is one rock ramp at the river Wiener at Rheinach. This is an unstructured rock ramp. It's 22 meters long, slope is 3%. More than 300 bullheads were marked, and also eels. and more than 4.4% of the bullheads and more than 49% of the other fish managed to reach the upper parts, the upper sections of the river. And of course, if you have any further questions, then you can ask Peter later on. This is an example that I'm more familiar with. This is still the River Wiener. This is still Canton Aargau. Two rivers merging. At that point in time, there was a weir, and that was fixed in such a way, but it had to be restored. So we built a ramp, a rock ramp. This is a picture from the bridge in the direction of the flow. This is against the flow, low water, and a slight flood. Those of you who will participate in the field trips on Saturday will see this ramp. Pit tack equipment at the beginning of the rock ramp. This is the upper part of the rock ramp. Here you see the antenna. So any fish with a pit tack will be detected. And here you see the box with the PC, etc. We caught 9 different fish, and we did this in 2 months. In 2012, the 9 fish, the barbus, salm, bulkheads, qualius, anguilla, gobio, etc. And the result is this. We marked almost 376 fish. More than 70% were detected above the ramp. 12% were redetected, but below the ramp, so they didn't make it. Oh, sorry, it was the other way around. Green, they crossed the antenna. Yellow, they were detected downstream, and 70% were unlucky. It was either because the antenna was broken because of the flood, or the fish drifted to other sections of the river. Once again, the figures with the different fish. The trout, about 60%. Found above the ramp, and here you see the percentages for the other fish, such as barbel and grayling. There was no passage found for some fish. Eel. There were, for eel we can't say anything, and for bullhead it was also not possible to say anything because the number wasn't high enough. The trout, they were the fastest, and the barbel was the slowest. And there was another fish that took more than 60 days. That was the loach. So we have to ask ourselves how long these field tests should be conducted, because some fish manage in a short time, but others simply take longer. This is another example in Pfaffnen, still Aargau, an unstructured rock ramp with a slope of 6%, which is the upper limit for passability. We had 2 types of fish that were marked, 3 types. The Schneider was found again, and we don't have any percentages because they were marked before in another exercise. For the bullhead, it was hardly possible because it was perhaps too steep, and they migrate also overnight. Here another ramp, which is more flat. 125 fish were marked, and those were bullheads and chop, and we were able to show that they actually passed. There was no delay in the upstream migration. With these figures, we would want to show that unstructured rock ramps allow fish to pass this particular ramp. From the field tests and the experience of Armin Peter's group, we can make a general recommendation with respect to the possibility for fish. Steep ramp, more than 6% only in trout regions without any small fish. Structured ramps must be preferred vis-à-vis classical ramps. First of all, they are usually quite steep, so the flow rate is very high. And with these block carpets or rock carpets, they are quite homogeneous in comparison to unstructured rock ramps. In regions with other fish, such as the grayling, the ramp should have less than 3%, and in the barbel, less than 2% or somewhere between less than 2 to 5%. As a matter of fact, there should not be any barriers in the ramps. This is something that could be examined also theoretically, but only in the field you can actually prove whether passability is guaranteed or not. As a summary of my research, I'm giving you this flow chart here, which is giving you the dimensioning concept for unstructured rock ramps. I just brought it along as the conclusion of my work. The idea is that an engineer who doesn't know about anything about fish can use this flow chart in order to plan an unstructured rock ramp. The idea is, well, this is not only an idea. We are preparing a practical implementation together with the company Flussbau AG. They will consider that, and the Swiss agency is supporting them in their efforts, and they also supported my paper. I'm quite sure that there is a further potential with respect to river construction and ecology. But from the point of river construction, I'm quite sure that it could be studied when the ramp is most stable. What happens in a curve? Can you work with rocks of different sizes, etc., etc.? And from an ecological point of view, it might also be necessary to determine what kind of heterogeneity you need in order to guarantee passability. It is most important for both industries to cooperate, the ecologists with the engineers, so to speak. Otherwise, you build only stable ramps that are not passed, or the other way around. And therefore, I would like to thank Armin Peter for his support, and I would like to thank you for your time.